Hello and welcome back. We had just started looking at the difference quotient in the previous video, and I do want to revisit why it is that we're looking at this. Again, we want to know what the slope of essentially a curved line is, and our approach is going to be, well, if I want to know the slope at a particular point along any graph, it doesn't matter if it's a straight line or if it's curved, what we'll do is we'll look at f of x, and we want to know, we want to take the slope at a point that's very close to it. So one point very close to x is going to be x plus a hair, x plus just a little bit. So we'll just apply our slope formula and look at the difference in height between our 2 points and the difference in the x values. Well, x plus h minus x, x's cancel, and what we're left with is our difference quotient. So this is a slope, again, difference in the height of a function divided by the difference in how far we've gone over, so rise over run. And we did a few examples, and we'll start to notice some patterns here. So let me put these in red. So we started with the function f(x) is equal to x squared. We got 2x plus h. Our next function was x cubed plus 4x. We got 3x squared plus 3xh plus h squared plus 4. And then the last one we had to do a little bit of work for, but the algebra all checks out. We had f of x was 2 over x, and we ended up getting minus 2 over x times x plus h. So again, we just had a couple of fractions that we had to consolidate. So if we want to find the instantaneous rate of change, meaning we want to find the slope at exactly 1 point, we're just going to let h approach 0. So again, if we want to find the slope, we have to take 2 points, and we're looking at rise over run. But if we let those 2 points get closer and closer and closer together, as in we let this hair that we've scooted over get really small, what we do is we'll call that the instantaneous rate of change. So it's going to be the slope at exactly that point. So let's go through a couple of examples. So let's find the instantaneous rate of change of f(x) is equal to x squared at when x is equal to 1. So we did find the difference quotient of x squared before. So the difference quotient was 2x plus h, I believe. So let's come back up and check. Yes, 2x plus h. And let's plug in some values and see what's happening here. So let's say that x, we've got some values for x. We want x to be 1, and we're going to let h approach 0. So what are some values that we can plug in here? Well, we know that we want x to be 1, so let's plug in four values, and then we want h to be approaching 0. So let's let h approach 0. We'll plug in 1, plug in 0.1, 0.01, and 0.001. Well, what's happening to our difference quotient? In essence, our slope. Well, the difference quotient, if I plug in 1 for x and 1 for h, I'll get 2 times 1 plus 1 is 3. If I plug in 0.1, 2 times 1 is 2 plus 0.1, and the same trend will continue. 2 plus 0.01, 2.001, and we can see that we're getting closer and closer to 2. So if we really want to let h approach 0, all we have to do is take a limit. So at 1, at x is equal to 1, the difference quotient is going to be equal to 2 times 1 plus h. Right? So here's our difference quotient at exactly x is equal to 1. then what we can do is we can just take the limit as h approaches 0. So the limit here, well, this is pretty straightforward. 2, the limit of 2 is just 2. It's always 2, it's a constant function. And as h approaches 0, h approaches 0. So this is just going to be 2. So when we draw our parabola, for f of x is equal to x squared, and we come out here to our point 1, the instantaneous rate of change, the slope right there, is equal to 2. And that's it. So that's how we find the instantaneous rate of change. So let's look at this one here. So we have the instantaneous rate of change of f of x is equal to 1 over x at x is equal to 2. Well, first of all, we have to find the difference quotient. So let's find the difference quotient for this guy. So we want f of x plus h minus f of x over h. Plug in x plus h into our function, we get 1 over x plus h minus f of x itself over h. Again, I've got some fractions on top, so I'm going to do some scratch work off to the side to consolidate those fractions. So if I have 1 over x plus h and 1 over x, I need them to have the same denominator. So let's multiply the top and bottom of this guy by x. And let's multiply the top and bottom of this guy by x plus h. And we subtract these guys. What we'll notice is that we'll have x minus h over x. That's x minus h. And the x's will cancel. So this is going to be equal to minus h over x times x plus h, all divided by h. Well, again, this means that we'll put this on the bottom of the fraction. Oops. X times x plus h, and the h's cancel. So we do a lot of work for the following. Negative 1 over x times x plus h. Cool. So I want to find the instantaneous rate of change at x is equal to 2. So I just want to draw a quick picture just to remind ourselves what exactly it is that we're doing here. We have our function 1 over x, and it does something like this. And then if we come out here to 2, here's where we want to find the slope of this point, the instantaneous rate of change there. Because the slope isn't going to be constant forever, we want to find the slope exactly at that point. Well, we can see that it's kind of going down there, so we might expect a negative slope. And our difference quotient hints at that because we've got a negative sign. So let's plug in 2 into here, and let's let h go to 0. Again, we're trying to find the slope between 2 points, so we might as well take a point and a point really, really close to it. So the difference quotient at 2 is going to be negative 1 over 2 times 2 plus h. So far, so good. And now I want to let these points get closer and closer and closer together. Because right here we're at 2. Over here we're going to be at 2 plus h. I want to let that hair shrink to 0. So these guys are going to get closer and closer and closer together. So let's take the limit as h approaches 0 of negative 1 over 2 times 2 plus h. When we look at this, what we see is that the top is going to be a polynomial. It's just a constant function. The bottom is going to be a polynomial in h. We're just multiplying some h's and some numbers together, so it's going to be a polynomial. So what I can do is I can just plug in 0. And this is going to be negative 1 over 2 times 2 plus 0. 2 plus 0 is 2, so we get negative 1/4. Which makes sense. If we look at this point here, we can see that we're going down. The slope here is decreasing, so it should be a negative number. But also, we're not decreasing all that fast, so it's not going to be some really big negative number. We're going down fairly gently. So negative 1/4 kind of makes sense based on our picture. Now, in fact, what we have been doing is we have been finding the derivative of a function. So you may have heard this word, you may have taken other calculus classes before, maybe not, but here we have introduced the derivative. And the derivative of a function is going to be the function that describes the instantaneous rate of change. So again, all a derivative is a slope. So again, the derivative, we're basing it on the difference quotient, which is going to be f of x plus h minus f of x all divided by h. Again, this is going to be the slope part. We have 2 points, f of x at x, and then we're going to scoot over just a hair, and we're going to look at the point x plus h, and then f of x plus h. It's just slightly different. But we want those 2 points to be as close together as possible, so we take the limit as h approaches 0. The hair that we scooted over, we want to be even smaller than before. This is our definition of the derivative. So let's go through a couple of examples. Let's find the derivative. So the derivative sign that we use is just going to be a prime. It's going to be an apostrophe, essentially, that we put after the function name. So let's find the derivative of x cubed. Well, first of all, we have to find the difference quotient. So let's find the difference quotient. We have f of x plus h minus f of x all over h. Cool. When we plug in x plus h into here, we're going to have x plus h cubed minus x cubed all over h. When I cube this guy, again, I could just do this in some scratch work. I'm going to get x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed over h. And we'll notice a few things cancel. X cubed minus x cubed. And what's left over, we'll have some h's in here. So after I divide by h, this is going to be 3x squared h divided by h. That's just 3x squared. The next one, 3x h squared divided by h. 3xh. And the h cubed divided by h is going to be just h squared. Everything else has canceled out. And so this is going to be our difference quotient. And what we want to do is we want to take the limit. So let's do that. So I've got the derivative is going to be the limit as h approaches 0 of our difference quotient, which we already solved, 3x squared. Plus 3xh plus h squared. And here, this is where we'll have to be a little bit careful. H is going to 0. But what is happening to x? The answer is nothing. X is just going to be constant here. We're not changing x at all. X is just going to represent some number. So what happens here? Well, this last term, h squared is going to go to 0 as h goes to 0. As h gets really small, that's going to go to 0. 3 times x times h, as h goes to 0, the 3x, it can't compensate for this. So this whole term is also going to go to 0. This term is going to go to 0. And what we're left with is 3x squared.